All right. So this is going to be homework or process dynamics, work 5, part A. Can't really see that up in the corner oh well. So first question, show algebraically that the amplitude ratio and phase lag of two transfer functions in series are the product and sum of the amplitude ratio and phase lags of individual transfer functions respectively. Okay, so basically what that means is we have, so here's our general format. The amplitude ratio, which equals the new amplitude over the original amplitude of any kind of system, equals the square root of the imaginary part squared plus the real part squared. And where the real and imaginary part come from, that comes from when you evaluate the typical first order transfer function. S equals I omega. And then you eventually get the imaginary part and the real parts to that equation. Let me double check the problem statement one more time. Okay, so yeah, just basically any two transfer functions. So let's show fundamentally what their amplitude ratio and phase lag would be, and then we'll compare that to what's being argued. So fundamentally, we have two different transfer functions in series, and whenever they're in series, it's pretty straightforward. You just multiply them together. So G1 times G2. And when we would do this, we would take their imaginary part of G1 plus I plus R1, and then imaginary part of the transfer of the second transfer function plus the real part of the second transfer function. All right. So we'll go ahead and multiply that out. I should have had my R's first, but it's okay. So when we multiply that out, we have negative I1 times I2 plus imaginary number I1 R2 imaginary number I2 R1 and then plus R1 times R1. Or R1 times R2. Also, I'm going to specify here at the top, I have a trig principle that we're going to use later, and we'll see why. That's going to be for phase lag. Please focus. All right. So let's separate out our imaginary real parts. So we'll have our real parts to the left plus I times I1 R2 plus I2 R1. Okay, so this is our real part right here. This is our imaginary. And like we said, for any kind of system, the amplitude ratio follows the format of your imaginary part squared plus your real part squared. So our amplitude ratio would be equal to, this is going to get really, really messy. It'll be R1, R2 minus I1, I2 squared plus I1, R2 plus I to R1 squared. All right, so bear with me, guys. The focus is not working. Also, I'm going to have to do a lot of algebra. So, and we're just going to, the square root's going to be there. I'm just not going to keep writing it out. So R2 squared. Gosh, I feel like I can't do basic algebra in my head right now. Minus 2 I1 I2 R1 R2 plus I1 squared I2 squared. All right, so that's the first part. Plus, goodness gracious, I1 squared R2 squared. Oh my gosh. I'm sorry, my brain is just not working today. I'm going to have to boil this out. Goodness gracious. I2 R1. Plus I1 I2 R1 R2 plus I1 R2 I2 R1 plus back here at the end I2 squared R1 squared. Goodness gracious, now you see why everybody uses a shortcut. Okay. These two sum up together, and that's 2 I1 I2 R1 R2. And that cancels out with this over here. And I think that leaves us with AR equals squared plus 2. No, not plus 2. I I1 squared I2 squared. Okay, so based off just our basic principles, we know that that should be the amplitude ratio of two of our process functions in series. So let's look at what the argument is on the next page. So what they're arguing is that the sum of our amplitude ratio, so our first amplitude ratio equals the square root of I1 squared plus R2 squared. And our second amplitude ratio equals, goodness gracious, I2 squared plus R2 squared. All right. So what we're arguing is that the overall amplitude ratio should simply equal the product of these two amplitude ratios, the square root of this one times the square root of this one. So let's start squaring those out. I apologize if you cannot see my subscripts. I'm trying to do this to the best of my ability. All right. So here's what we're left with. We're left with, and this is a mouthful, I1 squared times I2 squared plus I1 squared times R2 squared plus I2 squared times R1 squared plus R1 squared times R2 squared, all square root equal our new amplitude ratio, which is the same thing that we had back here. So yes, that is in fact true. Now on to the next argument, which is the phase lags of two of these in series can simply just be added up. So how would we say this? A phase lag 1 plus phase lag 2 equals the tangent of our overall system's phase lag. All right. Where do we want to start with this? So we take, or wait, how about this? So to actually find phase lag, first of all, let's prove what it is fundamentally. I keep forgetting where we're supposed to go first. So we would have we would know that, so this is overall. So our tangent phase lag overall equals our imaginary part over our real part. And we know from what we just derived earlier, our imaginary part is this, and this is our real part. So let's write that out. So for our overall system, we have I1 R2 plus I2 R1 over R2 R1 minus I1 I2. So we have to prove that this right here would equal our phase lags whenever they're like separated by addition. So here's what we'll do. We have tangent 1, tangent phi 1 plus phi 2, and that's the same thing as sine phi 1 plus phi 2 over cosine phi 1 plus phi 2. What we can do from here is we can use our trig identities. So we also know that sine of phi 1 plus phi 2 equals sine of phi 1 times cosine of phi 2 plus sine of phi 2 times cosine of phi 1. And then on the bottom we have cosine of phi 1 plus phi 2, and that equals cosine of phi 1 times cosine of phi 2 minus sine of phi 1 times sine of phi 2. So where we go from here, we divide both sides by this cosine of phi 1 times cosine of phi 2. That'll give us, up here, it'll give us sine of phi 1 over cos. So I'm not going to do all the algebra, but the cosine of phi 2 over cosine of phi 2 cancels out, so we're left with tangent of phi 1 plus this over here, which would leave us with tangent of phi 2. This divided by this is simply 1, minus this right here, which is tangent of phi 1 times tangent of phi 2. Well, we know right here, we know fundamentally that tangent of subscript I equals our imaginary part subscript I over our real part subscript I. So we take this relationship. We have I1 over R1 plus I2 over R2. 1 stays the same. And this is I1 over R1 times I2 over R2. So from here, we multiply everything by R1 times R2. That gives us I1 times R2 plus I2 times R1 all over R1 times R2 minus I1 times I2. And this right here is the exact same expression as our overall tangent that we argued that it would be. So that's it for the first part. All right, next part. Show algebraically that the phase lag of a first order system, I don't know how to pronounce that word, approaches 90 degrees. So we'll start with our good old basic formula of a first order transfer function. So k over tau s plus 1. So what we'll want to do is have s equals I omega. That gives us k tau I omega plus 1. Now, we want to eventually get to our phase lag, which means we'll need the tangent phi, which is our phase lag, of our imaginary over our real part. So we need to separate this out into our imaginary and our real parts. So what we're going to do is we're going to multiply the top and the bottom by the reverse conjugate. So that would be 1 minus TWI. So on the bottom, we're left with negative cancels out. Plus, oh, it's not T, it's tau. I'm stupid. You guys knew what I meant. Tau omega I, tau omega I. Tau squared omega squared over 1 and then minus or plus I negative tau omega 1 plus tau squared omega squared. All right. Do they want the phase lag or the amplitude ratio? Phase lag. Okay. So we have our imaginary part. We have our real part. So our tan phi would equal our imaginary, which is going to be k negative tau omega over 1 plus tau squared omega squared over 1 plus 1 over 1 plus tau squared omega squared. So these cancel out. K's also cancel out. And we're left with tan phi equals negative tau omega tan inverse. We have negative tan of tau. Negative tan inverse tau omega equals phi. And just by basic trigonometric understanding, I guess, we know that this can. Can it only get to 90? No, it can't get to 90 degrees because the cosine. Yeah, cosine would go to 0. So this can only get as close as possible to negative 90 degrees. Alrighty. Next part, show algebraically that two first-order systems in series will always yield an overdamped second-order system. Okay. What we have going on is we have two first-ordered processes, so GP, and so GP1 and GP2. And we know that our transfer function for that is K1 over tau 1s plus 1. And then this one is K2 tau 2s plus 1. All right. So we multiply these out. So GP1, GP2 equals K1 times 2 tau 1s plus 1 tau 2s plus 1 K2 squared plus tau 1 plus tau 2s plus 1. All right, so what we're interested is this right here, the tau 1 plus tau 2. So we're going to set tau 1 plus tau 2 equal to 2 times zeta, and then the geometric mean of both of those. So the square root of tau 1 times tau 2. What we are interested in is our zeta, which is our dampening coefficient. So what we'll do is we will square everything on both sides. So we have tau 1 squared plus 2 tau 1 tau 2 plus tau 2 squared equals 4 zeta squared times tau 1 tau 2. And for this system to be overdamped, that would mean that this right here would always have to be, our zeta would always have to be greater than 1. So if we set zeta equal to 1, and then move everything over, we would have to prove that that expression is greater than 0. So we set zeta equal to 1. We have tau 1 squared plus 2 tau 1 tau 2 plus tau 2 squared equals 4 times tau 1 tau 2. So we move this over, set this equal to 0. Here. Sorry. This must be greater than. Greater than 1. All right, so move this over. This then becomes tau 1 squared minus 2 tau 1 tau 2 plus tau 2 squared is greater than 0. How do we prove if this expression is greater than 0? Well, we can factor these, and we're left with tau 1 minus tau 2 all raised to the second power is greater than 0. Assuming that both of these aren't equal to 0, they can't be, and that both of these are not equal to each other, we know that this expression has to be greater than 0. So it is overdamped if it's second order. All right. So this next part, derive algebraically the phase lag for a pure time delay transfer function. So look at a pretty straightforward piece of a process. So we have our process function, and then we have our time delay function. And this follows the general format of e raised to the negative theta times s. So what we'll do, s equals I omega. So we have e raised to negative theta I omega. So what we can do with this is we can actually follow a trig function. So we know that this equals cosine theta omega plus, or I think it's minus. Yeah, minus I sine theta omega. Well, what can we do with this? Well, right here we have our imaginary part and our real part, and we're looking for our phase lag. So again, the formula for phase lag, the tangent of our phase lag equals our imaginary number, our imaginary part over our real part. So the tan phase lag equals negative sine theta omega over cosine theta omega. And what does sine of something over cosine of the same thing equal? That's negative tan theta omega. So then if we want to get phi is simply equal to the tan inverse of what's on the other side, which is negative tan theta omega. And the inverse tangent of something inside a tangent function is simply what's inside the tangent. Simply what's inside the function. So our phase lag is equal to negative theta omega. All right, so last part of Part A. So computationally show and explain how a first-order system with a time delay may become unstable with proportional-only control. So like we said, I don't think this was stated earlier, or I guess it was. The phase lag of first order can only approach negative 90 degrees, so that means that it won't go unstable. But when it has a phase lag, and everything does have a phase lag, it becomes unstable. And we're gonna show why. So let's plot out our Bode diagram. So that's going to be the same thing that we were doing on all these other ones, except we're going to have a theta. So that's going to be, I think we'll just set that to 0.1. We don't have to worry about simulating our process. And like we said, it's only first order, so it's not going to be raised to the third power on the bottom. But it is going to be multiplied by that expression that we saw for a time delay, which is going to be our exponential, or our e, exp, and that's raised to negative theta, and then it would be negative theta s, but we're setting s equal to j omega. Everything. So then we'll plot that out. Oh, we also have, I don't think I mentioned, we have our proportional controller as well. So we're going to show when we just have that, it becomes unstable. 4, 4, 4, 4, 4. All right. So as you can see, when we look at our phase lag, like we talked about with when we talked about our first order one, that's only supposed to go, it shouldn't even go to negative 90 degrees. This one goes way past it because it has that exponential due to the time delay, which just causes that phase lag to keep growing. I think it just grows to negative infinity because you can see it just steeps down like this. That's what causes it to become unstable. So that's the end of 5 Part A.